In these lectures, we shall study the series expansions of functions and their numerical evaluation. Now, how many functions are there? Well, if you look at a decent mathematical table, you usually have about 3 pages of different functions in small print. So there are lots of functions. But elementary functions are few in number. If we really exaggerate, we might say 27. There is this power function. Then there are 6 trigonometric functions. And there is logarithm. There is exponential. Then we have 6 hyperbolic functions. Then we realize that ln x and exponential are inverse functions of each other. The power function is its own inverse function, but we should have 6 inverse trigonometric functions and 6 inverse hyperbolic functions. So that's 27. But when we try to economize a little bit, we realize that the hyperbolic functions are nothing but the exponential function. We will return to this. So we can reduce this to 21. But then, if hyperbolic functions are so intimately related to the exponential function, then of course inverse hyperbolic functions will be related to logarithm. So we can economize a bit more. 15. Then how about trigonometric functions? Trigonometric functions are also related to the exponential function. So we go down to 9. And inverse trigonometric functions are related to the logarithm. So we go to 3. What are these 3? Again, the power function, natural logarithm, and exponential. Now this 27 was an exaggerated number in the first place. Okay, for trigonometric functions. Suppose we have sine, and with a little bit of pushing around, cosine. Then who needs tangent? Tangent is just sine over cosine. So it is nothing new. How about secant? Well, it's 1 over cosine. So who needs that? And the inverse trigonometric functions are also related to each other. Inverse sine and inverse cosine add up to 90 degrees. So we should reduce the number as much as possible. Then comes the point. We say, can we reduce this to 1? And, just the power function and even more specific integer powers. So that's our question mark. Well, the Maclaurin approach is an attempt in this direction. Can we express functions as a sum, well, in fact, an infinite sum of integer powers of x? So it's a good attempt. Let's try that. We write our wishful thinking first. We say, let f of x be a constant plus another constant times x plus another constant times x squared plus another times x cubed, so on and so forth, all the way to infinity. How do we get these coefficients? A0, A1, A2, A3 is the question mark. Well, let's go one by one. A0 is rather easy because if I set x equals to 0, f of 0 equals a sub 0. All these powers of x die out. How about a1? For a1, I want to eliminate this x, and also I don't want a0 to remain. Why? Because to eliminate this x, if I divide by x, this will be singular. So what's the thing to be done? Let's take a derivative. A0 vanishes. I have a1 plus 2a2x plus 3a3x squared and infinite the other terms. Well, if I evaluate this derivative at x equals to 0, then all these terms will die except for a1. I'll have f prime of 0 equals a1. We shouldn't jump to conclusion and say f double prime of 0 will equal to a2. No, it's a bit more complicated. To get rid of this and leave a2 alone, f2 double prime of x equals 2a2 plus 6a3 x and other terms. While we are at it, let me get the third derivative, which is simply 6a3. So f double prime of 0 is 2a2. F triple prime of 0 equals 6a3. I think we have enough information to realize that the coefficient, general coefficient a sub n, first of all, is the nth derivative evaluated at 0. A0 is the zeroth derivative of f evaluated at 0. A1 is the first derivative at 0. A3 is related to the third derivative at 0. But we should divide by n factorial, because 6 is 3 factorial, 2 is 2 factorial, 1 is 1 factorial, 1 is also 0 factorial. Therefore, f of x can be written as a summation starting with n equals to 0 to infinity, the nth derivative evaluated at 0 divided by n factorial x to the nth power. Now, is this correct? Not quite, because we cannot use it for many functions that have peculiar properties. But still, it's a good start. But I'll say this is the Maclaurin expansion. And I will say do not use it unless really necessary. We should only do this for simple functions and get the others by other methods. Now, one has to be systematic not to make mistakes. the thing is, we should have a table. Here we should have n, and we should start with 0, 1, 2, 3, and 4, let's say. And here we should have the nth derivative of x, and here we should have the nth derivative evaluated at 0. Now, the function that we are expanding is right here. Now, what is the simplest function that we would like to expand? Well, if we choose e to the x, that's the function 0th derivative, etc. All derivatives are e to the x. I'm not saying much about the exponential function. The only thing that is important to us, that its derivative equals to itself. Well, 1, 1, 1, 1, 1. Because e to the 0 is always 1. So, e to the x is 1 plus x, 1 times x, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial times x cubed, plus 1 over 4 factorial times x to the 4th, so on and so forth. Now we will use this later on to evaluate e. Right now we don't know anything about the numerical value of e. How about e to the minus x? E to the minus x is obtained from the exponential series by changing x into minus x. Nothing happens to 1, x becomes minus x. But minus x squared is also x squared, 1 over 2 factorial x squared. The cube changes sign, and nothing happens to the 4th power. Now we are ready to do a hyperbolic function. Let us say cos x. Cos x is nothing but e to the x plus e to the minus x divided by 2. So, sort of, it is the average value of these two series. 1 and 1, average is 1. X and minus x, they add up to 0. 1 over 2 factorial x squared, 1 over 4 factorial x to the 4th, etc. So all the even powers of x divided by their factorials. How about sinh x? Well, sinh x is e to the x minus e to the minus x divided by 2. So it will be the difference divided by 2. Ones will cancel. X minus minus x is 2x, but divide by 2, it is x. Then it will be x cubed over 3 factorial plus x to the 5 over 5 factorial, so on and so forth. We could also get this result by differentiating cos. Derivative of cos is sinh. So x squared over 2, when you differentiate it, is x. X to the 4th over 4 factorial, when you differentiate it, will give you x cubed over 3 factorial. So this thing is quite self-consistent. Now let me say this Maclaurin, that is easy. Those were the easy ones. We finished those. Then there are some hard. Then there are harder. And then there are impossible cases. Well, let's do one more easy case. Let me do sine. Sine x, what I write here, zeroth derivative of sine is sine itself. The first derivative is cosine x, another derivative minus sine x, another derivative minus cosine x, another derivative sine x. How nice, because we start with sine x, and at the fourth step we also have sine x. So this is a pattern that repeats itself. So what about the thing at 0? 0. This is 1. This is also 0. This is minus 1. Again 0. So this 4 will repeat itself. And it is not all that difficult to write it down. Sine x will be 0 times 1, okay. Then 1 times x divided by 1 factorial, which is x. Then 0 times x squared term, minus 1 x cubed over 3 factorial. If we repeat ourselves, it will be x to the 5 over 5 factorial minus x to 7 over 7 factorial, so on and so forth. How do we get cosine? Well, cosine x we should get by simple differentiation. Derivative of x is 1. Derivative of x cubed is 3x squared. So this is minus x squared over 2 factorial plus x to 4 over 4 factorial, etc. So, easy cases. One thing that should attract our attention is the hyperbolic function, sich, was the same thing except these minuses were also pluses. Cosh, hyperbolic cosine, was the same thing, only these minuses were replaced by pluses. So there is this intimate relation between cosine and hyperbolic cosine, sine and hyperbolic sine. The names are rather suggestive. Then we finish the easy functions. Let's go to hard cases a little bit. For example, we know, as you see, sine and cosine. How about tangent x? Well, for tangent, we can go through the same motions here, writing tangent, then getting its successive derivatives. But you realize that tangent x, just like sine, is an odd function, which means I get a contribution every other term. X squared, x to the fourth, x to the sixth will not appear. But I have to take each derivative, even if I don't use it. There is a simpler method, writing tangent x as sine x over cosine x. Well, let's do a very primitive thing first. Sine x is x minus x cubed over 6 divided by cosine x, which is 1 minus x squared over 2. Of course, higher terms like x to the fourth we disregard. So x to the fourth equals to 0 kind of thing. So what do? I multiply top and bottom by 1 plus x squared over 2. So the denominator is 1. 1 minus x squared over 2, 1 plus x squared over 2 is 1 minus x to the fourth over 4, but x to the fourth we disregard. How about this? First, x outside x cubed over 2, inside minus x cubed over 6. Then last is x to the 5. So we disregard that. So this is simply x, then plus 1/2 is larger than 1/6, 1/3 x cube. Well, this is a good start, but is this accurate enough? Perhaps not. Perhaps we should be more accurate. So let us say we should add here x to the 5 over 120, and here we should add plus x to the 4th over 24 for factorial. Now, 1 over 1 minus delta, delta being a small number, is 1 plus delta square plus delta cube, etc. This is the geometric series. This is the sum. So I write this as like that. So here I'll have the numerator x minus x cubed over 6 plus x to 5 over 120 multiplied by 1 over 1 minus delta, which will be 1, plus delta x squared over 2 minus x to the 4th over 24 plus delta square x squared over 2 minus x to the 4th over 24 squared. This is actually simpler because here, in expanding this, I'll have a term x to the 4th over 4. Then the cross term is x to the 6. Here, as you see, we did not go all the way to x to the 6. So this is a regime where x to the 6 is neglected. And x to the 4 squared is x to the 8. So forget about it. So this is simply x to the 4 over 4. Well, x to the 4 over 4, which is 6 divided by 24 minus 1. So this is plus 5 over 24 x to the 4th. We should do this. Well, we can do it long way. We will have 9 terms, 3 times 3. But let's have a more practical approach. Let's have a table like this. Now, here I'll have 1 minus 1 over 6 and 1 over 120. Here I'll have 1, 1 over 2, 5 over 24. So let us just multiply the coefficients. 1, 1 over 2, 5 over 24. That was easy. Minus 1 over 6, 1 over 120. That was also easy. This is minus 1 over 12. What about these? I don't care, because you see this minus 1 over 6 is the coefficient of x cubed. And this is x to the 4th. So that's x to the 7. We throw it away. So these are nonsense. We disregard them. How do we add these? We add these diagonally. How? Well, 1. So tangent x equals to x. Then 1/2 minus 1 over 6. We know that. That's 3 over 6 minus 1 over 6. 2 over 6 or 1 over 3 x cubed. Well, this is a bit more difficult. We should go all the way to 120. So this is 10 over 120. And this is 25 over 120. So 25 minus 10 is 15. One more, 16. 16 over 120. This simplifies by 8. So this is 2 over 15. So plus 2 over 15 x to the 5. And other terms. Well, it was somewhat more difficult than sine or cosine, but still it's doable. So we did the hard. Let's do the harder. Cosecant x. Cosecant x will not allow us to use the Maclaurin routine, writing the function its derivatives and evaluating them at 0, because cosecant 0 is infinite. So what should we do? Well, we should use the fact that it is 1 over sine x. So we should go 1 over x minus x cubed over 6 plus x to 5 over 120. Or let me factor out an x. Then I'll have a 1. Then minus x squared over 6 minus x to the 4th over 120. So it is the same approach. I'll have my 1 over x and 1 over 1 minus delta, hoping delta is a small quantity. Smaller than 1 is good enough. 1 plus delta square and other terms. So I'll go 1 plus delta, which is x squared over 6 minus x to the 4th over 120. Then plus square of this. But of course, square of this is simply x to the 4 over 36. The cross term, x to the 6 is out of question. X to the 8 is totally out. So the thing is to combine these. So this will be 360, 10, and this will be 363. So it will be 1 over x times 1 plus x squared over 6, then 10 minus 3 plus 7 over 360 x to the 4th. Well, now let us write 1 over x plus x over 6 plus 7 over 360 x cubed and other terms. Now here you see our original approach of having a table of the function and all its derivatives, then evaluate them at 0, wouldn't work at all. Here we have a problem. What is that problem? It's this term. But at least we know how singular it is. It's 1 over x. So we know that. Well, this is of course not Maclaurin. This is what is called a Laurent expansion. Now, at this point, it's a good idea to test oneself. Homework. How about cotangent x? What's the expansion of that? So we did the easy sign. We did the difficult or hard tangent, harder cosecant. Now let's go into the impossible. A good thing for impossible is, for example, logarithm. Logarithm ln x evaluated at x equals to 0 is minus infinity. Ln 0 is minus infinity. Its derivative at x equals to 0 is infinite. Another derivative minus infinite. So it's all infinities. It can't be done that way. Well, moral of the story, it just can't be done. Another and surprising thing is, for example, square root of x. You cannot expand it in integer powers of x around 0. I will not go into the details, but we understand this on the complex plane where z equals to 0 is a so-called branch point for x to a non-integer power or logarithm function. So what do? We give up the idea of expanding x to the power, let's say, nu, but we do 1 plus x to the nu. Nu is some non-integer power. So again, we go to our table, and 0, 1, 2, 3 should be enough. Then here I have the nth derivative, and here I have the nth derivative evaluated at 0. The function that I'm considering to expand, I write here. The 0th derivative is the function itself. 1 plus x to the nu. What about its first derivative? Nu times 1 plus x to the nu minus 1. Another derivative, nu minus 1, 1 plus x to the nu minus 2. Another derivative, nu minus 1, nu minus 2, 1 plus x to nu minus 3. Getting uglier and uglier. But no problem, when I set x equals to 0, 1 to any power is 1. Here, nu, 1 to any power is 1. Then nu minus 1, and nu minus 1, nu minus 2. So we go like this. So 1 plus x to power nu equals 1 plus nu x plus nu minus 1 x squared over 2 factorial plus nu minus 1 nu minus 2 x cubed over 3 factorial and such terms. This is the so-called binomial expansion. Let us do a physics problem related to this. The famous, but unfortunately misleading equation, E equals to mc squared, as used by Einstein 110 years ago. But this m is not our m. The m we use nowadays is the so-called rest mass. Einstein's m was actually m divided by 1 minus v squared over c squared. So that's the idea. So energy is mc squared times 1 minus v squared over c squared to minus a half. Downstairs and square root. So we go mc squared 1, then the power times this v squared over 2 c squared and other terms. I will not give them because I plan to give it as a homework problem. So this equals mc squared plus mv squared over 2. This is the so-called rest energy, kinetic energy, and other terms. Now the first term is the so-called first order relativistic correction. So what does this equal to? Homework problem. Now you realize I did most anything except for logarithm. Now this is a very important principle which we will never forget. Do not use unless really necessary, the Maclaurin formula. Another thing is never expand an inverse function. But what one should do? Expand its derivative and integrate. Here I should say there might be integration constant. So x equals to 0 is an ugly point for the logarithm function. So we don't expand ln around x equals to 0. So we expand it around x around 1. X equals to 0, but the argument is 1. So how do we expand this? We don't. We go its derivative, or let me do it formally, ln 1 plus x d dx equals 1 over 1 plus x, which is either you can use the binomial expansion formula 1 plus x to the minus 1, or simple geometrical progression. This is 1 minus x plus x squared minus x cubed plus etc. So ln 1 plus x is the integral of this, which is x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 and many other terms. Now here, let me digress a little bit. Let me take the value x equals to minus 1. What happens then? Well, I'll have ln 0 equals minus 1 minus 1 over 2, minus 1 over 3, minus 1 over 4. So overall minus, I'll have 1 plus 1/2 plus 1/3 plus 1/4, the so-called harmonic series. And knowing that ln 0 equals to minus infinity, we realize that the harmonic series diverges. It adds up to infinity. Let's do a bit more. For example, another inverse function, inverse sine. So we go d dx sine inverse x equals 1 over 1 minus x squared square root, or 1 minus x squared to minus 1/2. What is this? This is 1, then plus x squared over 2, then minus 1/2, then minus 3 over 2, nu minus 1, divided by 2 factorial. So that's 3 over 8 x to the 4th. And other terms, but this should be sufficient. So inverse sine x expands into x plus x cubed over 6 plus 3 over 40 x to the 5 and other terms. Inverse tangent is 1 over 1 plus x squared, which is 1 minus x squared plus x to the 4th. So inverse tangent is x minus x cubed over 3 plus x to 5 over 5. Very simple. How about inverse hyperbolic? Its derivative is 1 minus x squared in the denominator, which is 1 plus x squared plus x to the 4th, and therefore hyperbolic tangent inverse x is x plus x cubed over 3 plus x to 5 over 5. At this point, I'll do something strange. I want natural logarithm of 1 plus x divided by 1 minus x inside the square root. So this is actually 1/2 ln 1 plus x, then minus ln 1 minus x. ln 1 plus x we had done. So this is 1/2. ln 1 plus x was, its derivative was 1 over 1 plus x, which is 1 minus x plus x squared. So this was x 1 minus plus x squared minus x squared over 2 plus x cubed over 3 terms. Then If I wanted to go further, I would have minus x to 4 over 4 plus x to 5 over 5. Now, from this, I will subtract ln 1 minus x, which is the same series, only x replaced by minus x. So this will be minus x squared over 2, minus x cubed over 3, minus x to the 4th over 4, minus x to 5 over 5. Now, let's get rid of all these minus signs in the parentheses and make this a plus sign. So, let's add up. This thing equals to x and x. They add up, but divided by 2, it's a single x. Minus x squared over 2 plus x squared over 2, they cancel. X cubed over 3's add up and remain. X to the 4 terms cancel. X to the 5 terms also add up. Now, remember this was ln square root of 1 plus x divided by 1 minus x, which is, as you see from here, is inverse hyperbolic tangent x. As I said in the very beginning, that hyperbolic functions are intimately related to the exponential function, and inverse hyperbolic functions are, of course, intimately related to the natural logarithm. It might be a good idea to write down every inverse hyperbolic function of x in terms of natural logarithm. It is not an extremely difficult problem. You do one, the rest will be easy, but we should be very careful of how we start. Like this approach was somewhat lucky. We came up with a result, and then out of nowhere, I came up with a logarithm expression, and we saw that they were the same. But suppose there is nobody to help us to come up with a logarithm that will do the thing. So there must be a general method to get that. So we go like this. Inverse hyperbolic tangent x equals ln of a function of x. So x equals hyperbolic tangent of ln f. What is hyperbolic tangent? It is sig e to the ln f minus e to the minus ln f divided by 2. But if I divide by cosh, that will have a 2 upstairs. It will be e to the ln f plus e to the minus ln f. So this is f minus 1 over f divided by f plus 1 over f, or simply f squared minus 1 divided by f squared plus 1. Remember, this equals to x. So f squared minus 1 equals f squared x plus x. Regrouping, f squared is times x minus 1 equals f squared x minus 1, or 1 minus x, that's better. Taking this to here, and this equals to 1 plus x. So f equals square root of 1 plus x divided by 1 minus x. So there are 5 more. And the biggest surprise comes when you study the logarithmic version of inverse hyperbolic cotangent x.